Hi 3E. Today is the one period lesson again. I've prepared this video clip uh, because I can't be physically present this week for this one period. Nevertheless, I prepared this video clip for revision on mass, weight, density, and inertia. Just as I promised that we should spend this week to start our revision. Okay, so mass, weight, density, and inertia was was a topic that you learned last year when you were in Sec 2. So allow me to quickly browse through a summary of some key important points, and then you will try a few questions to recall how to calculate them and answer them. Okay, so let's start. In this video clip, you would be able to open up uh, this slide. Um, as I go through this with you, not to worry that you have no hard copies to um, note down, because I would be printing this copy for you when I come back. Meanwhile, because the number of questions are not a lot, the examples are not a lot, and it is a revision, later on when there is some work example, you just try to work on it on a piece of paper or on your iPad first, and then just to check the answer whether it's correct or not. When I come back again on Thursday, I will print all this stuff for you, so not to worry. So meanwhile, just try to go through in sequence with me. Hopefully, this one period lesson is not wasted, so that even though I'm not with you, by following this, it can help you recall some important points about mass, weight, density, and inertia. Okay, let's start with the key differences between mass and weight. There are four key differences. So on the left column is our mass, and the right column is our weight. So the first thing is the definition itself, the definition. So the first definition, the first part of the definition for mass, okay, for mass will be um, it is the amount of matter that made up a body. Yeah, the amount of matter that made up a body. So the mass of our body, let's imagine our own, is made up of our organs, tissues, muscles, bones. Okay, so these are the amount of matters that made up uh, the body, our body. All right, and weight, if you remember, is the pull of gravity on a body. Okay, the pull of gravity on a body. So if you recall, the second differences is that mass does not change from place to place. Yeah, mass does not change from place to place. The mass measured on Earth is the same as that on Moon, since the amount of matters that made up the body do not change. So, uh, just take our own body as an example. Whether I'm on Earth or whether I'm on Moon, the amount of matter, the organs, the bones, the fluid, the tissue that made up my body is still the same as uh, it didn't change when I go to the moon. Okay, all these things that made up my body does not change um, from place to place. So that's why mass does not change too. Okay, when you go from place to place, whereas weight does change from place to place depending on the G value. A lot of students like to call this G value the gravity value. It's not called gravity value. It has a proper name. It has a proper name called the acceleration of free fall. It's called the acceleration of free fall. Okay, this G value is not called gravity value. It's called the acceleration of free fall. And the G value change from place to place. For example, the G value on moon is smaller than that on Earth, right? Hence, the weight on the moon is also smaller than that on Earth. Okay, I repeat, because moon is smaller than Earth, it has a G value that's smaller. Remember, what is the G value on Earth all the time? Our G value on Earth is always 10, right? The G value on Earth is always 10. Okay, G value on Earth is always 10 meter per second square. All right, but the G value on Moon is always about 1.67 meter per second square. Okay, much smaller than that on Earth. And because this G value on Moon is so much smaller, when we measure weight of the same body on Moon, it will be the measurement will be much smaller. Okay, so weight changes from place to place, but not mass. Okay, the third differences is the unit of measurement. Okay, the mass is measured in kilogram, and here is where you have to know that 1 kilogram is 1,000 gram. Huh? Okay. So 200 gram. These are things you have to know. I cannot be going into it, but you know. So therefore, 200 gram will be equals to how many kilogram? Do you multiply or divide? You're changing from gram to kilogram. You have to divide, right? You have to divide. Okay. So it will be 1, 2, 3, 0.2, 0.20 kilogram. At least two significant figure. And please note that the SI unit for mass is kilogram. Okay, SI unit for mass is kilogram. The second part, the difference in units of measurement, of course, for weight is that it is measured in Newton. Okay, it is measured in Newton. SI unit is N, capital N. Sometimes, some of you remember in this way, 1 kg equal 10 Newton. Actually, it comes from the, the big formula W equal mg, which you already know long time ago. And the G value on Earth, again, I cannot stop emphasizing this. G value on Earth is always 10, right? So a quick example will be, from this point on, you will have to know how to convert mass to in kilogram to weight in Newton. Okay, weight in Newton. So here is where you see 3.5 kg, right? 3.5 kg in mass to convert to kilogram, to convert to Newton in weight. Okay, to convert to weight in Newton, it will be 3.5 kg multiplied by 10. W equal mg. M is the 3.5 and G is the 10, and then you get your 35 Newton. Okay, so very quickly we come down to the next difference. The next difference is the instrument of measurement. For mass, we always use a beam balance. Those sensei that use that measure the medicines that they collect, they always use the beam balance. Yeah, so beam balance help you measure the mass. Of course, in today's world, you have the modern time, you have the electronics balance. However, for instrument for measuring weight is spring balance. All right, those people who collect the newspaper for recycling and you bring to the recycling corner, when you need to measure what is the weight in Newton, you always use the spring balance, right, to hang on those stack of newspaper to see how much it weigh. Okay, then compression balance are those that you see in the wet market or even in supermarket. Sometimes you see those compression balance at the counter. All right. So these are examples of instruments. Next, let's quickly come to the practice. The basic requirement that you must have for your WA2. Okay, let's recall. For your WA2, first example, I start with level 1. Level 1, first example. Okay, a mass of my body, the mass of my body is 48 kg. That's my mass. Given the acceleration of free fall, the g value on Earth is 10. They always will put this statement just to let you know the g value on Earth is 10 for this question. Okay, and that on Mars, the g value of Mars, that on Mars. Okay, that on Mars, that means the g value of Mars is 3.75 meter per second square. Okay, sometimes this g value they put 10 meter per second square, sometimes they put 10 newton per kg. They are all the same. Okay, it's the same. All right. It's still talking about the g value uh measurement. So calculate my weight, my body weight on Earth, on Earth. Okay, on Earth. So which g value do you use? You know there's only one mass you can use, right? Okay. So which g value should you use at the right place? So this is level 1. The basic you must know for your WA2. Okay. I give you 30 seconds to try it yourself. Can your calculator press and check now? 30 seconds. Let's go. Okay, time's up. What is your answer? Okay, let's see. Did you get this? 480 Newton, yeah? Okay, 480 Newton. Just a quick check. Of course, on Earth, if I want to find my weight on Earth, it will be W equals to mg, and all I need to do is take my m, 48 kg, times my g value on Earth, that's 10, and I will get my answer. All right, okay. So next, calculate my weight on Mars. Okay, so calculate my weight on Mars this time. You should be very warm up already. Give you just 20 seconds. Can 20 seconds quickly get your answer in. Okay, time's up. What is your answer? Did you get this? Did you get 180 Newton? 180 Newton. Okay, so to show you how we arrive at that, again, it will be W equal mg. And my m has to be still, although I go to Mars, my mass must still be the same. Huh? My mass don't change. Doesn't matter where I go. My mass never change, so it's still 48 kg. But my g value change from place to place, right? The g value of Mars is, as mentioned above, is 3.75. 3.75. You multiply by that, you should get 180 Newton. Okay, all right. Okay, so this question, simple as it is, tests you a little bit about using the formula correctly, and number two, whether you know that the same mass is to be used in another planet, and whether you know to use a different G as given in the question. All right, now let's go to one level higher now, one level higher, but still manageable. Again, whether it's level 1 or 2, these are the basics you must know for your WA2. Okay, so I will again, just now previously, I would have marked a star. I should mark a star here so that you remember. Okay, this one, I will also mark a star. Okay, so that you remember these are important things. The weight of a dumbbell, the weight of a dumbbell was 150 Newton. You should not put M for this. This is weight, so it's W. Given that the acceleration of free fall on Earth, again, the G value is 10 meter per second square. Calculate the acceleration of free fall G value on Moon. G value on Moon. What is the G value on Moon? This time this G value is what you want to calculate. If the same dumbbell weighs 24 Newton on Moon, weighs 24 Newton on Moon, how would you calculate this? Okay, so I will have a situation here. Uh, Let me try to draw this. Okay, maybe I give you 1 minute to try this. 1 minute. Okay, ready? 1 minute to try this now. 1 minute, ready, go. Okay. Okay, ready? Okay, time's up. Okay, time's up. Did you get this answer? Please check. You can either write your answer in 1.6 meter per second square or Newton per kg. We are talking about the G value on Moon. Some student may thought that it is understood what the G value on Moon is 1.6. Can't I just put 1.6? You are required to calculate in the question. Show your calculation. So let's see. Let's see. So whoever did not get this, let's take a look. So I have Earth, I have Moon. Okay, I have Moon. I have the Moon. Yeah. So on um on Earth, the weight of the dumbbell is 150 Newton. That's the weight. Okay. And on the Moon, the weight is 24 Newton. Okay. Of course, the G value on Earth is equals to 10. But the G value on Moon is what we need to find out. We don't know. Okay, we don't know. So to calculate this G value with the W, again, I stick to the formula W equal mg. So I put a gm to represent the G value on Moon. So the G value on Moon, based on the formula, is W over m. Swap the m down, is W over m, which means it's 24 Newton divided by the mass. However, the mass on Moon is not known. The mass on the Moon is not known. I don't know what is this. If it's known, the problem is solved. Okay. However, this Moon, the mass can also be calculated from the Earth. Okay, can be calculated from the Earth because the mass on the Earth and the mass on the Moon should be the same. No change, right? So using here on this side now, W equal mg. Let's calculate the mass so that later you can bring it to the Moon to calculate. So the mass equals to W over G. W 150 Newton over the 10, which is 15 kg. Now this 15 kg can be used. Okay, this 15 kg now can be brought back here to use. So it becomes 24 Newton Okay, 24 Newton over this 15 kg. And there you get your answer 1.6. Alright, meter per second square. Yeah. Okay, so this is one level higher lah. Okay, now okay, let's move on now because time is catching up. Let's recall density. Density by definition of a body is the mass per unit volume of a body. So formula very, very important. And in your this WA2, this one is needed. Okay, for your calculation, it is measured in kilogram per meter cube for SI unit. However, sometimes your question also require you to know it in non-SI unit, meaning instead of kilogram, the mass you are given is in gram, and then the volume is all given in centimeter cube. So that's why it's good to know also that it can be measured in gram per cm cube also. Okay, all right. Uh, but SI unit you must stick to this. If it is SI, it must stick to kilogram per meter cube. Okay, how can density be affected when a metal is heated? Temperature rise. In most cases, when metal is heated, you must know how it leads to the change in the density. First of all, any metal when it is heated, it will gain heat and expand. Now, what does expansion means to you? Okay, that means the shape, in terms of shape, in all in all ages at all sides, it becomes larger, which means the volume, length and breadth and height will also increase. If the volume increase, but mass, remember the mass always remain constant. Yeah, mass always remain constant, right? Okay, and because of that, density decreases based on this formula. Okay, based on let's see uh, density equal mass over volume, right? If my volume keep increasing, that means this number gets bigger and bigger. My volume gets bigger and bigger, but this one stay the same all the time. The same number dividing by a bigger and bigger value, what will happen to your density? Your density will decrease or become smaller and smaller because you're taking the same mass to divide by a bigger and bigger value as you heat it. So vice versa, when you talk about cooling a metal, okay? When you cool a metal, the density also goes opposite, it will increase. Same reason, because this time it lose heat and it contract. Okay, when you gain heat you expand, when you lose heat you contract, so your volume decreases. If your volume becomes smaller and smaller and your mass remains the same, same mass dividing by a smaller and smaller value, then your density will increase. Okay, so this is something that you have to know at your standard as well. Okay, will density of a metal be affected? Will density of a metal be affected when the body is subdivided or enlarged? Let's say you already know the density of a substance or of a metal. So if I cut this metal into half, this body into half, will the density change? Then the answer here says no. But you must know the reason why. Of course, the density will not change because of the formula again. If 40% of the mass is removed, let's say I cut away 40% of a known metal, which I already know the density. If the mass is reduced by 40%, then its volume will also be removed by 40%. Okay, so mass over volume will remain the same because the numerator and the denominator each minus away 40%, right? Each minus away 40%. Then when you divide, it will remain constant. Your density will remain the same. Okay, so there are questions in O level that ask you, if I give you a metal plate that has a density of, let's say, 20 gram per cm cube, okay, metal plate, and I drill 5 holes into the metal plate, will the density change? The answer is no. Okay, it will still remain at 20 gram per cm cube. Okay, there will be no change. Some explanation goes into the definition, looks at the definition, because density measured by uh, mass per unit volume. I don't care how you subdivide the metal, we are still looking at per cm cube of the metal. So it will always be the same. Okay. Okay. Now next, how does density affects floating and sinking? Okay, something that you learned before. Again, when density of a metal is greater than when density of a metal or substance is greater than the density of a liquid, when you put the metal into the liquid, it will sink. This is something you must know again. When the density of a metal is smaller than the density of the liquid, it will float. Okay, it will float. So there are three different layers of floating and sinking you must know lah, to be able to tell very clearly, very quickly, whether the density is equal to, greater than, or less than water. So like substance A floating so high up here. So the density of A is less than that of water. Okay, whereas C sink to the bottom, so density of C is greater than that of this glass of water. But density of B floating in the middle always means, in American it means Z, neutral buoyancy. But in our physics, we just say that the density of B is equal to the density of the water. Okay, in this glass. All right. Okay, let's have a quick practice. A small rock is placed, okay, in the measuring cylinder until it is fully submerged. Okay, that means the rock sink to the bottom. The two diagrams shows the water level before and after the rock is submerged. Before and after the rock is submerged. The mass of measuring cylinder with its content is 200 gram initially. So with this, uh, the mass of the measure with its content, with this liquid, uh, before the rock is before the rock is put in, the mass this mass is 200 gram with its content, means with this liquid lah. But after the rock is put inside, okay, the rock is put inside, okay, the rock is put inside, the mass is now 366 gram, okay, 366 gram, okay, with the rock inside now. Okay, the level, in case you cannot see, I put there for you. It rise up. At first it was at 35 cm cube. Then after you put the rock in, it's 59 cm cube. Okay, 59 cm cube. Okay, so with this value, uh, in the picture, can you calculate the density of the rock? Only one question. Okay, only one question. What is the density? Can I give you quickly 1 minute to do this question? 1 minute starting now. Okay. Okay, ready? Okay, let's stop. Let's stop here. Did you get your answer? Did you get this answer? Let's check the answer. 6.92 gram per cm cube. Okay. Let's check how it is done. Okay, let's check how this is done. Yeah. Okay. So first of all, I want to calculate the density. I must know mass over volume, right? So let's talk about the mass first. The mass of the rock will be equals to the 366 gram minus the 200 gram. Okay, that will give you 166, 166 gram. And of course, the volume will be the higher level when it was dropped inside, 59 minus 35. That should give you 24 cm cube. Yeah, correct, 24 cm cube. Okay, now with that, you can calculate and get the answer. All right, now next, if the same rock is cut into half, what is the density of each half of the rock? Okay, so some student may think that you have to take 6.92 divide by 2. No. Okay, like we said, when you cut it into half, mass and volume each reduced by 50%. So based on the formula, mass over density, you will get back the same value. Same. So remains the same at 6.92 gram per cm cube. Okay, something that you have to know. I see it tested that quite often. Okay, when the same rock is dropped into liquid metal, very heavy metal, yeah, okay, liquid metal, the rock is likely, this rock, this piece of rock that you measured just now is likely to float on this liquid metal. Can you give a reason why? Okay, how 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 to say, how to give a reason why the rock float is likely to float? Okay, uh can you verbalize your answers to yourself? What do you think? What should I talk about? The density. Okay, was that in your thought? Let's look at the answer. One, two, three. The rock has lower density than the liquid metal. That's why it floats. Okay? So you must know when to bring in your answer to talk about density. Okay? In your answer, when to bring in density. Okay? All right? Okay, next. Finally, inertia. Hope is something that you have learned before also, but it's quite common sense. And there's not much. You notice that I have no questions about this to ask, but the word example itself are questions. I mean all the things that I mentioned here are actually questions in the O level already. Okay, so I quickly bring you through what inertia is about lah. Inertia of a body is its reluctance to start moving when it is at rest, and its reluctance to stop when it is moving. Okay, so reluctance to change is called inertia. Some people say, when you ask them when they are lying on the bed, you want to pull them out of bed because the alarm has sounded, you want to pull them out, and it's very difficult. They say, wow, my inertia is very strong. Okay, it means I feel very, very reluctant to wake up, right? So reluctance means, inertia means the reluctance to change the current state that you are in now. Okay, and this sounds very much like Newton first law. Newton first law. If I can relate it to force, it sounded very much like Newton first law. Why do I say that? Let's recall what Newton first law said. An object at rest will remain at rest. Then reluctance to change. Okay? And an object in motion will continue in the same motion. So reluctance to stop now. Okay? So it is quite it is quite the same as Newton first law. Okay, except there's no calculation for inertia. So what does the O level always ask about? Inertia. Inertia, when does it come in? Okay, it is the reason. Inertia is the reason why a passenger falls forward when a bus come to an abrupt stop. The passenger's reluctance to stop causes him to fall forward. Okay, very quickly show you the picture here. There, the picture on the left. Okay, when the bus is moving, at, let's say, 50 kilometer per hour, your body will also be moving with the same speed. However, when the bus suddenly come to a stop, 0 kilometer per hour, then your body will continue to move at the same speed, 50 kilometer per hour. So that's why you will fall forward. Okay, the inertia to change. Similarly, when you are at first you are standing at 0 kilometer per hour. Okay, you are standing at 0 kilometer per hour because you are not moving. When the bus is not moving, you are also at rest with the bus, at rest. Okay, however, once the bus start moving at 20 kilometer per hour, suddenly start moving, your body would still want to stay at rest. That's why you will fall backward. So that again has got to do with inertia lah. All right, inertia. Your inertia causes you to fall backward. The first diagram is your inertia cause you to fall forward. Okay. Then this last example here is about pulling a tablecloth away very quickly. If you can do that very quickly, you have seen this kind of trick before, and all the dishes that you prepare on the table can actually remain un uh, it can still remain on the table, okay, without spilling over or things like that. All right. So back to your notes, right? Back to the notes. A passenger falls backward when the bus start moving. The passenger's reluctance to move this time caused him to fall backward. Okay, you can. So the third example, you can pull off tablecloth without pulling off the dishes on the table. All these are some examples that O level like to use. That is hinting you on the word inertia. Okay. Now, a, a little bit of things more important about inertia is that inertia is very closely related to mass. In fact, inertia is mass itself. Okay, is mass. The greater the mass of a body, the greater the inertia to changes, the greater the reluctance to changes. For example, comparing a running puppy and a running elephant. Okay, you can imagine that in your mind. Okay, and I ask you to try to stop both. Who is harder to stop, right? Who is harder to stop? Of course, it is harder to stop a running elephant because his mass is much bigger, many times bigger than a puppy, and even you get a chain, you get a chain to hold on to him. It will be the elephant that pull you along. You won't be able to stop him because the greater the mass of a running body, the greater is its inertia to stop or to change. All right. Now, the last point is also very important. Okay, all these are important. Of course, not important, I wouldn't have put inside here. Okay, since mass of a body does not change, okay, we are still talking about mass, right? That's why inertia is put together with this topic because it's closely related to inertia. Okay, it's closely related to mass. Okay, since mass of a body does not change from place to place, the inertia of a body also will not change from place to place. What does that mean? If it takes 200 Newton to push a 5 kilogram box on Earth, okay, for example, if this is the box, which is 5 kilogram, and it takes 200 Newton for you to push on Earth, how much force will it take for you to push it on Moon? Some people may think that on Moon it will be lighter, so easier to push. But at the same time, when you go to the Moon, your body also is lighter, huh? And the mass of the box and you remains the same, huh? All right. So because mass don't change, inertia also don't change. That's why it will also take 200 Newton to push the same box on Moon, huh? On Moon, even though it should weigh lighter on Moon. Okay. The reason is because okay, the mass of the box does not change on Moon. Hence, the inertia does not change. The inertia means is reluctance to move when you give it a push. Since the reluctance is the same, therefore the amount of force that you need to move it will still stay at 200 Newton. So it's with the same ease. Okay, sometimes O level use the word it is with the same ease, with the same ease, with the same force, with the same ease in pushing. You will be pushing the box with the same ease. Okay, that's all for this short revision. Thank you. If you cannot finish hearing this in school during this one period, you can continue. It doesn't take long. You can continue to hear it at home. All right, that's all for here now. Thank you very much.